Welcome to DNAmaker. This automated platform is designed to build long DNA molecules that encode digital information. Rather than saving files to magnetic media, we write data as sequences of nucleotides, then physically assemble those sequences into continuous DNA molecules that can be amplified and read. To accomplish this at scale, DNAmaker integrates three coordinated units: a programmable pipetting robot for liquid handling and molecular reactions, a rail-mounted robotic arm that transports plates across the platform, and a robot-accessible refrigerated storage. Throughout this video, you will meet the DNAmaker robots, see how DNA is assembled for digital storage, and follow the workflow step by step. At the heart of our DNA storage platform is the OpenTrans OT2, a precise, programmable pipetting robot. In practice, the OT2 takes charge of the biological workflow, preparing master mixes, managing incubations, and running PCR, thanks to its dual pipettes, temperature-controlled modules, and integrated thermocycler. Molecular biology reagents can be tricky to handle. They're often cold and viscous, flowing slowly and clinging to pipette tips, sometimes even trapping air bubbles. To deal with this, the OT2 applies finely tuned pipetting parameters. Tip immersion depth is controlled with precision to avoid air intake, while aspiration and dispense speeds are slowed down so the liquid can move smoothly. Extra programmed actions, like blowout to expel any remaining drops, touch tip to clear the exterior, and short pauses to let the liquid settle, all contribute to reliable handling. In our automated workflow, temperature control is critical. Reagents, enzymes, and assembled DNA are stored at 4 degrees Celsius in a robot-accessible refrigerator, with a motorized door. This controlled cold storage preserves reagents and products between steps, and ultimately enables fully unattended operation. The Dobot MG400 robotic arm is mounted on a linear rail to physically link platform modules. Fitted with a custom 3D printed gripper, it shuttles 96 well plates between the OT2 pipetting deck and the refrigerated storage. Reagents, DNA, and reaction products are delivered to the OT2 when required, and returned to chilled storage when idle, preserving the cold chain. By removing manual transfers, the Dobot serves as the DNAmaker platform's transport backbone, enabling fully automated, closed-loop workflows. Beyond hardware, DNAmaker relies on software orchestration to coordinate all modules. At the center, the OT2 acts as a hub. Its Raspberry Pi controls pipettes, thermocycler, temperature modules, and even the motorized fridge via USB. On top of this, a local server runs directly on the OT2, linking the Dobot arm and its rail for synchronized control. From the operator's side, everything is run through a Jupyter notebook. Python code triggers pipetting, transfers, and fridge access in a reproducible workflow. Native Python libraries handle the OT2, while custom ones drive the fridge and Dobot. In practice, humans write the code and robots do the work. Now, it's time to put DNAmaker to work. In this demo, the platform will assemble 12 DNA molecules, each 3,600 base pairs long, from 96 smaller fragments, then amplify them by PCR. And the data encoded? A cornerstone of history. The Universal Declaration of the Rights of Man and of the Citizen. The first stage of the DNAmaker workflow to build and store this text document is the Golden Gate assembly. Here, enzymes cut and join DNA fragments with high precision. You can think of it as putting together the pieces of a digital file. Small blocks of information are combined into complete DNA molecules. With the principle explained, let's now follow the workflow step by step as it runs on the DNAmaker platform. Step 1. The robotic arm transfers the 96 well plate containing the DNA fragments from refrigerated storage to the OT2 pipetting robot. To limit evaporation, plates are fitted with a self-closing seal and placed on the automated thermoelectric module set at 4 degrees Celsius. The transfer takes less than 1 minute. Step 2. The OT2 pipetting robot prepares the assembly master mix using the NE Bridge Golden Gate assembly kit, which contains the restriction enzyme BSA1 and T4 DNA ligase. All reagents and reaction tubes are maintained at 4 degrees Celsius on an automated thermoelectric module. To improve temperature stability and limit evaporation, the microtubes are immersed in water. After all reagents are added, the master mix is thoroughly homogenized. Preparing the mix for a single reaction takes about 2 minutes. Step 3. The OT2 pipetting robot distributes the reaction master mix into separate microtubes, one for each molecule to be assembled. From this step until the end of the protocol, pipetting orders are randomized to avoid any bias between microtubes and plate wells. The distribution takes about 1 minute per molecule to build. Step 4. The OT2 pipetting robot adds DNA fragments from the 96-well plate to the microtubes containing the Golden Gate reaction mix. Each reaction receives an equimolar amount of all fragments to be assembled, with DNA concentrations adjusted to remain within the pipette's most accurate range. Adding one fragment from the 96-well plate to a microtube takes less than 1 minute. The video clip shows the assembly of 12 molecules, each built from 8 unique fragments, requiring a total of 96 pipetting steps. In principle, a multi-channel pipette head could be installed to accelerate the process, but its use depends on the specific robot configuration and available pipette slots. Step 5. The robotic arm transfers the 96-well plate containing the DNA fragments from the pipetting robot back to refrigerated storage. An empty 96-well plate is then placed on the automated thermoelectric module set at 4 degrees Celsius. The exchange takes about 1 minute. Step 6. The OT2 pipetting robot transfers the reaction mixtures to the thermocycler and launches the Golden Gate assembly incubation. Incubation lasts 1 hour and 30 minutes, alternating 5-minute cycles at 16 degrees Celsius and 37 degrees Celsius. The incubation period is skipped. Transferring each reaction to the thermocycler takes approximately 1 minute. Step 7. Once incubation is complete, the OT2 pipetting robot transfers the assembled DNA molecules into the 96-well plate retrieved from refrigerated storage. The transfer takes about 1 minute per molecule built. Finally, the 96-well plate containing the assembled molecules is stored in the refrigerator by the robotic arm. The transfer takes about 1 minute. The second stage of the DNAmaker workflow is PCR, the process that multiplies our assembled DNA. In digital data storage, redundancy is essential, just like saving several copies of the same file on a hard drive. By creating millions of identical DNA molecules, PCR ensures that the information can be read reliably, even if some molecules are lost, damaged, or contain small errors. Step 1. The robotic arm transfers the 96-well plate containing the PCR primers from refrigerated storage to the OT2 pipetting robot. As previously mentioned, plates are fitted with a self-closing seal and placed on the automated thermoelectric module set at 4 degrees Celsius. The transfer takes less than 1 minute. Step 2. The OT2 pipetting robot prepares the PCR master mix using the Q5 Hot Start high-fidelity DNA polymerase from New England Biolabs. All reagents and reaction tubes are kept on an automated thermoelectric module set at 4 degrees Celsius. As previously mentioned, the reaction microtubes are immersed in water to improve temperature control and reduce evaporation. Once DNA polymerase, reaction buffer, and DNTPs are added, the mix is thoroughly homogenized. Preparing the master mix without the PCR primers and DNA matrix takes about 2 minutes for one reaction. Step 3. The OT2 pipetting robot distributes the PCR master mix into separate microtubes, one for each DNA molecule to be amplified. From this step onwards, pipetting orders are randomized to avoid any bias related to the order of microtubes and plate wells. The distribution takes less than 1 minute per molecule to amplify. Step 4. The OT2 pipetting robot adds PCR primers corresponding to each DNA molecule to be amplified to the corresponding microtubes. The addition takes less than 4 minutes per molecule to amplify. Step 5. The robotic arm transfers the 96-well plate containing the PCR primers from the pipetting robot back to the refrigerated storage. The 96-well plate containing the assembled DNA molecules is then placed on the automated thermoelectric module set at 4 degrees Celsius. The exchange takes about 1 minute. Step 6. The OT2 pipetting robot dilutes the assembled DNA molecules to a concentration compatible with the PCR. Then, it transfers it into the PCR reaction mix of the corresponding microtubes. Dilution and transfer take 3 minutes per molecule. Step 7. The robotic arm transfers the 96-well plate containing the assembled DNA molecules from the pipetting robot back to the refrigerated storage. An empty 96-well plate containing the assembled DNA molecules is then placed on the automated thermoelectric module set at 4 degrees Celsius. The exchange takes about 1 minute. Step 8. The OT2 pipetting robot transfers the complete PCR reaction mix to the thermocycler and launches the PCR reaction. The transfer takes 1.5 minutes per PCR reaction mix. The PCR reaction takes less than an hour. Step 9. Once the PCR reaction is complete, the OT2 pipetting robot transfers the PCR products into the 96-well plate retrieved from the refrigerated storage. The transfer takes about 1 minute per PCR product. Finally, the 96-well plate containing the PCR products is stored in the refrigerator by the robotic arm. The transfer takes about 1 minute. DNAmaker demonstrates how integrated robotics and bespoke engineering can make the fabrication of long DNA molecules practical and reproducible for information storage. By combining precise liquid handling, custom robotic transfer, and robot-accessible cold storage, the platform reduces variability and increases throughput, both essential to move DNA storage beyond laboratory demonstration. Next steps focus on increasing throughput by shifting from fragment-based storage to oligonucleotide pools, and on making the platform more autonomous by automating the DNA sequencing stage. Our goal is to turn DNA storage into a robust, operational technology for preserving digital information.